All right, and when we're talking about the resistance of a conductor, particularly with wires, there are going to be four main factors that influence that resistance. The first is length, and as length increases, the resistance also increases. So if we have a quick little graph, we'll say resistance versus length, it's going to be a direct relationship. And length, again, is measured in meters. As far as cross-sectional area, if I want to draw a quick little wire, this would be the length. Let's see how good my 3D drawing is. If we're talking about cross-sectional area, that is the cross-sectional area measured in meters squared. And as that increases, the resistance decreases. So if we have a little graph, resistance, this is area, it's going to be an inverse relationship. Sketch something like that. Material, that's going to be given to us by the Greek letter rho. That's called resistivity. And as you see on the next page, those are given values. And temperature. And as temperature increases, resistance increases. An example where we're looking for the resistance, and resistivities are specific to particular temperatures, so they will denote that, and resistivity will go up as temperature goes up, as I mentioned in the previous slide. So here, formula we're given, resistance is equal to resistivity, Greek letter rho, times length over area. And we look on the chart, we're talking about a copper wire. So I'm going to use this number. Now we're going to plug in. And now it gives us our radius, so we actually have to calculate what the cross-sectional area is. Remember, the area for a circle is pi r squared. So we're given the radius, so I'm just going to leave the bottom as pi times the radius squared. Enter that in my calculator, and I should get a resistance of 1.68 times 10 to the negative 4. Well, which wire has the least resistance? And remember our analogy of electrical current, where it's easiest for current to flow, it has the least resistance. If we picture water flowing through either a hose or a pipe, where water is our electrical current in the analogy, we want the shortest, the thickest, if possible, made of silver, and the coldest wire or conductor. And this doesn't take into account material or temperature. So when we look for the shortest and the thickest wire, we get this choice. Relationship I want to show before moving on so we can finish up these notes is, if we think back to power, in order to have power in your lifetime, you have to work overtime. We can think about it a few different ways. If we connect our potential difference formula is equal to work over charge, or if we want to plug in, we can rearrange this and get work equals charge times potential difference. We could take that and plug it in here, and we get power equals Q times V over time, where Q over T is equal to current from the beginning of this packet. So we get power equals I times V. And just by rearranging Ohm's law, again, which is R equals V over I, you can rearrange this a bunch of different ways, and plug in, and all of these are equivalent. So V squared over R. And lastly, if I could squeeze it in here, would be I squared times R. So if we look at the example, a light bulb connected to a 3-volt power source draws 0.5 amps of current. What is the power delivered to the bulb? So we know power equals IV. Three volts. So we should get 1.5 watts of power. And then how much energy? Remember, energy is work, which we can rearrange this formula and get work equals power times time. Plug that in. We got the power, which is 1.5 watts. Times the time, 3 minutes. But remember, we don't care about minutes. We want to convert that to seconds, so 3 times 60. Multiply that out, and we should get 270 joules of electrical energy.